section 3. Topics for today. We're going to look at an introduction to speed control of induction motors. So we're going to give it a little bit of a talk through variable frequency drives, inverters commonly used to speed control induction motors. So again, along the lines of last time, I went through some stuff about induction motors, which aligns with one particular type of motor you want to move using the assignment, give you an idea of the flavour, the type of thing that you need to be researching. So again, now I'm into the type of thing you need to be looking at with regards to speed control of a particular motor that you might choose, if speed control is needed for your particular application. Okay. Then we're going to have a look. We've already had the introduction to assignment 1. I done that last time. So then we're going to look at power calculation techniques where we got multiple loads. So how you would do the overall power on a load center, delivering power to a number of different loads, like 3 or 4 blower motors and a chiller, and so what you would do to calculate the total load on a distribution board, if you like. All right, and the way you can deal with that calculation. We'll also have a look at solving some circuit problems via the power triangle and power with complex notation. So some more maths and calculation type things towards the second half of the session. Alright, and again, got some tutorial questions for you to have a go at. And how are you getting on with the other ones that you've already had? Are there any that you've got a sticking point on that we need to flag up and go through, or? Well, if yeah, I mean, if you let us, if there is one that's particularly sticking, we can go through it together and just clarify. All right. Pass it again. So, speed control of induction motors. I'll give you last week's stuff in a little while, Gemma. All right. Popular way to achieve this is using AC adjustable speed drives, okay, sometimes called VFDs, variable frequency drives. They're commonly known as inverters, okay. Device available for about 20 years, suit a wide range of applications, from single motor pumps, fans and compressors to sophisticated multi-drive machines. They operate, we talked last time about the induction motor and how that's synchronous or close to synchronous with the AC frequency. So it relies on the frequency. If we run a motor at 50 Hertz, that'll run at a different speed to if we run it at 60. So these drives work on that fact. They'll vary the frequency, we vary the speed. Okay? Now, they are fairly expensive. They provide a high degree of control, and also they can save on energy. So the energy saving from them can help to offset that extra cost. Alright? And you can have precise control of speed. So instead of, for instance, on a impeller fan type application, instead of running the motor flat out and opening and closing the flap to vary the flow, you can actually run the motor at the speed you need to get the flow you want, for instance. Or a pump, you run the motor at the speed you want to get the flow you want. So the adjustable speed drives, variable frequency drives, number of different things to call them, okay. But what they are is electrical control device that change the operating speed of the motor. They're able to change that because they change the frequency. Basically, in a nutshell, what an inverter does is take the 3-phase AC mains, rectify it to DC with some rectification, and then use a microprocessor to recreate the 3 sine waves again. But the trick is, because they're created using a microprocessor, you can vary the frequency of the output. So in a nutshell, that's what an inverter is. It takes AC, rectifies it to DC, buggers about with it to turn it back into a variable frequency AC signal. Alright, so ignore and slip, we talked about last time. Speed of induction motor comes from the formula that involves frequency, 60F of the number of poles. So if we alter the frequency, we're going to change the speed of the motor. Yeah, I mean, you can see it from the 2 different systems that you get around the world. This country 50 Hertz system, so a 4-pole motor operates at 1500, but in Japan or America where a 60, that would operate at 1200 RPM. I got to be the wrong way around, didn't I? Oh, 40 Hertz I put there, not 60. Yeah, so it'd run faster in America on the 60 Hertz system. So by varying frequency, we can adjust the speed over a wide range or vary the speed using precise changes of electrical frequency input. So they are quite complex in terms of the electronics involved in recreating that variable frequency. We're able to program them so that they ramp up the speed and ramp down and all sorts of things, and control the braking, and quite complex programmable wise modern inverter drives. Power and torque. The inverters actually control both the frequency and the voltage simultaneously. So you get a constant voltage against frequency ratio, which keeps the current flow similar to full speed conditions. So by varying the voltage as well as the frequency, you work with a constant current. This allows the motor to draw full current at any speed and produce full torque as motor speed changes. If you allowed the current to drop, you'd lose torque. Yep. What happens to the power when we lower the speed and torque using frequency? We've got a formula there, can't remember where I put it. Torque in Newton meters, multiplied by, so power in kilowatts is torque times omega, which is your RPM, over 9549, which is a conversion factor. So, torque against speed gives you power. So if we reduce the speed, we reduce the power drawn and reduce the energy used. Yep. Because power relies on speed. So that's reduced cost. What about increasing speed? Some specifically designed motors can operate at higher than normal speeds at frequencies over 60 Hertz. However, there are some primary concerns. Was the motor or loaded drives designed to operate at higher speeds? I've experienced this with things like conveyors. Oh, we can run that conveyor really fast now because we can set the frequency to 70 Hertz, 80 Hertz. But was the mechanical system designed to operate at that high speed? Was the motor designed to operate at that high speed? Many are not mechanically set up to do so. So you could get premature bearing problems and such like if you try and run them more than their rated maximum speed. Secondly, inverters are not capable of increasing the voltage above the mains voltage. Therefore, as you increase the frequency above the design, your torque is going to drop off because you're not keeping that constant voltage to hertz ratio that I talked about at the beginning when you reduce the speed. We can't, as the frequency's going up, we can't increase the voltage any more than the 400 supply and therefore we're going to drop torque because the current's going to drop. Yeah. At some point it will lead to the motor speed decreasing despite you increasing the frequency, but it just can't get any more out of it. Okay, so they're the primary issues over running the thing faster or a higher frequency than is on the rating. That's as low it might sound. But like planetary gears looks. Yeah. Advantages and disadvantages. There are a number of both. The main advantages are the energy savings, the improved control you get over the process. Particularly, I mean, think back to the old way of start and stop in our conveyors at Fibre, and I'll start it up on a strict online starter and all the bottles fall over. Use an inverter and you can get it to ramp up the speed and they don't all fall over, for instance. Reduced voltage starting, so lots of different things can be programmed. Lower system maintenance. There's a bypass capability, and I'll talk in detail about that in a minute. And multi-motor control. The disadvantages start with the initial cost of the drive against what it would cost to buy a direct online or even a Star Delta starter. Motor heating at low speeds. Maintenance. The output harmonics and induced power line harmonics, each of which I've got a little bit about on in the forthcoming slides. Alright. And what I'm trying to do here is show you the basic thing I always go on to students about. Whatever you're choosing, whatever you're trying to pick, particular motor against another motor, you must have a balanced argument. You must consider both the advantages and the disadvantages of each of the things against each other. And not just kind of plump for that because that looks really good, it's got lots of good advantages, but what are the disadvantages? Because everything's got some disadvantages. Everything. Usually, in a lot of cases, that's down to cost, but... So, energy savings. Adjustable speed drives can save significant amounts of energy against traditional methods where the load or speed operation varies. They're among the most efficient types of speed control when used on axial or variable torque loads like centrifugal fans, pumps and compressors. So if you think about it, you're gonna gain the most if you actually need to speed those things up and down. If you've got a fan that's running 100% all the time and that don't need to run 100% all the time, then you're going to gain more than if you put a VFD on a fan that does need largely to run flat out most of the time or all the time. You're not going to gain very much. Okay. As the motor reduces the operating speed of the fan, pump or compressor, horsepower required to operate the system is reduced. So we're talking about savings again. Major advantage of the ASD, and one of the primary reasons they have become so popular in many process operations is the energy saving. Right, so although there's a high cost, what I will say, and I can't remember what I got on the slides about it, is reliability from my own experience is very, very high with inverter drives. We had a lot of blow molding machines with old style, what's called pillar motor, variable speed, big motors about this size. They varied speed by moving two com rings around. I think never really did work out how the theory of how they work, but I think they effectively altering the number of poles involved in operation. But they'd vary anything from the bottom revs to between two limits. They were constantly variable. But the cost of the brushes and the maintenance and the rewinds that we had to do, and we replaced two machines with inverter drives and induction motors and never touched them again the rest of the time I was there. So although there's that expense of buying quite an expensive drive, the motors aren't particularly expensive. That saving in maintenance is significantly higher, and because you're saving breakdown time then as well. So, variable torque loads require much lower torque at low speeds than they do at high. So part of what you're being asked to do is determine whether your application requires variable torque or whether it's a constant torque load. The torque required varies as the square of the speed, and the power required varies as when the speed of a variable torque load is reduced to 50%, the torque required to drive the load is reduced to 25%, and the horsepower to 12.5. So it's quite graphic how much that can reduce the power requirements when you reduce the speed that you're driving at. Right. Variable torque loads include most centrifugal and axial pumps, fans and blowers, and many mixers or agitators. Constant torque load requires the same amount of torque regardless of speed. So same torque whether you're running at 1% speed or 100% speed. Remains constant throughout the range. If the speed drops to 50%, then the power required to drive the operation will drop to 50%, while the torque remains constant. Alright, so you get a linear drop in the power required with constant torque loads if you slow down. They include conveyors, positive displacement and reciprocating pumps, compressors, things that lift the load like cranes. So the lifting part of a crane is going to be for a particular load, the load is going to be constant. I'll add a qualifier to that once you've got it moving, once you've got it accelerated up to speed. Advantages. Reduced voltage starting was mentioned. Acts like an ISD, acts like a reduced voltage starter to limit the amount of inrush current when the motor starts. You can generally limit, we all know when you start a direct online or a star delta motor, you've got an ammeter on there, the ammeter whacks over to full and then bounces back to a running current after a short period of time. The ASD can generally limit this inrush current to a maximum of 150% full load current. Second advantage, improved process control. You've got a solid state device which lends itself well to being integrated with control systems, control signals, so you can on the fly vary the motor according to the measured output pressure of a pump or something, so you keep a constant pressure. Can take control signals, start and stop signals, and outputs from PLCs to control at speed and so on. Other types of variable speed control can be very limited as to their interface into a process control system or have no capability whatsoever. So the VSD's inverter drives particularly good at that. Bypass capability. Many ISD systems make use of bypass starter in parallel with the drive. So what that allows is you to be able to switch the power to the motor through a direct online or star delta starter, so you can take the ISD out for repair or service. So if it does break down, they're fairly simple to bypass because you haven't made any significant changes to the rest of the system. It's still a basic three-phase induction motor. So if you really need, if that application is critical, you can have a parallel starter system to bypass the VFD if you need to make sure you keep it running like 100% of the time. I can think of maybe the applications like that when you're in campaign that you wouldn't want a particular system to break down. You might want to bypass for an alternative method of running it. Yeah. So older types of variable speed control are usually physically coupled between the motor and the load and must be uncoupled. So they require recoupling. So there are ISD can be bypassed in a matter of seconds, so you could have a switchover system for that. I do think now in reflection these slides have got a bit too much information on them, but never mind. We can have motor control, so you can buy ISDs that will control multiple motors from the same drive, which can be an advantage over other types of variable speed control device. Smaller physical size than having two separate ones, as well as a reduced initial cost of that system. It's unlikely to cost twice as much as two separate drives. We had a look at some advantages. How about the disadvantages? Well, initial cost. Not the best choice for all variable speed systems. Some of the drawbacks to using them are this initial cost of an ISD is generally greater than other types of variable speed control mentioned, and is a common obstacle for the process plant to install the ISD. Payback from energy saving has been the traditional justification used. However, improvements in process control are increasingly being considered. So, because the process control aspect of it has improved, then the saving is significantly more. As you use more features, you're effectively making a bigger saving, is what they're saying. The energy saving payback is generally low for applications where the average requirement is near the motor's rated speed. The gain on energy saving comes from being able to run the motor at 50 or 75% speed. If on average, you know, like for 3/4 or more of the day, that's running at full speed, you're not saving very much by having the VSD. As a general rule, a payback of 2 to 3 years typically justifies the purchase of a variable speed drive. Maintenance. Like any other solid state device, it requires specialist troubleshooting knowledge for operations and maintenance personnel. I wouldn't think that there's too many end user situations where they've got an engineering department that could on their own service and or repair directly the internals of any inverter motor drive. Because one, the manufacturer is very unlikely to give you the information. Two, whether someone at that level would have the skills and knowledge about that system to be able to fault find on it is debatable. So that you're usually talking about them going back to factory or kind of replacing a whole card module or parts of the system rather than to component level repairing of these drives. However, they do have quite a few diagnostic capability that's improved. So, you know, a lot of them will kind of tell you what's wrong with them a lot of the time, so that does help. They are quite difficult to get your head around the programming of them as well, because a lot of them have got kind of 200 or 300 different parameters you can adjust, and knowing what they all mean is sometimes a bit tricky. Okay, this for me, the next one, is one of the main disadvantages here: motor heating at low speed. Because most of your induction motors are fan cooled, so a fan on the back blows air over the fins of the motor, keep it cool. no matter what speed the motor runs, we've already said, so we can keep the torque constant, we keep this voltage frequency ratio the same, so that the current's the same. So we're going to get the same amount of heating from the current flowing through the motor at half speed as we do at full speed. But at the lower speed, the cooling fan is only going round at half the speed, so you're only going to get effectively half the cooling. So if the motor's producing the same amount of heat and the cooling's only half what it should be, you're going to have issues. So, as a rule of thumb, you generally take a fully loaded Class B insulation motor down to 50% speed on constant torque without overheating. So it's about the class of motor that you buy, the class of insulation. If you get a Class F insulation motor, you can go down to approximately 20% speed without overheating the motor. When a Class F insulation motor needs to be run below 20% speed on a constant torque application, the motor needs to be derated. It's because the cooling air isn't there. Yeah. Yeah, they'll provide you with a higher class of insulation then. It might do, because that's what it's talking about, is derating it. Saying, you know, we got to rate this power of this motor down and the current rating is down. Yeah. Well, after a short time, we made sure we locked out the programming of it, so there was a, like you say, a minimum and maximum to what the frequency could be set to. So try as they like, they couldn't go below no. So it might be the class of motor they put on it. Yeah. Yeah. Right, output harmonic distortion. Now, those of you that studied with me last year will remember us talking about harmonic distortion in electrical principles and doing some calculations around that. But the output electrical waveform generated by an ASD is not a pure sine wave, it's reconstructed sine wave. It includes what's called harmonic distortion. That means it's got distortion of higher frequencies than its actual frequency sitting on the top of the normal sine wave. So if this is the normal sine wave the VSD is meant to be producing, has actually got harmonic distortion sitting on the top and the bottom. Yep. Hopefully not too much. So you've got harmonics, they're multiples of the base frequency. So if we're running at 60 Hertz, your second harmonic will be 120 Hertz, your third harmonic 180, and so on. So each of those harmonic frequencies will have a current component to them that will create more heat in the motor. Yep. As a rule of thumb, ISDs will create between 5 to 8% extra heating in a motor compared to the same motor running straight off the mains of a sinusoidal waveform from the power line. One way to overcome this is to use a motor with at least Class F insulation or an inverter rated motor with Class M insulation. So you could be right, they might have learnt the lesson and decided they needed to change the insulation class of the motor. Yeah. Well, I don't know for sure. Yeah. As well as that, induced power line waveform distortion. This is again around the ASD being a solid state electronic load, and the fact that that's creating these waveforms by reconstructing a waveform using harmonics. It can cause waveform distortion to be induced on the input electrical power supply. So it can, what it can do is put harmonic distortion and notches onto the mains. It consists of both harmonic distortion and line notching. Harmonic distortion line notching are a result of non-sinusoidal waveform the drive generates. So it's again for the same reason, it's recreating this sine wave by quickly turning on and off DC power to create the waveform shape at a different frequency. So it pulls the current from the power line in pulses and cause these notches. This can severely distort the electrical power supply within the facility. If not properly protected, it can hinder the operation of other devices. So they have to be careful to filter this. Use filters to stop these VSDs putting these notches onto the mains, because other sensitive electronic equipment won't like it. Yeah. Yeah. Interfere with them. Yeah. Because if also another use of inverter is where people have solar panels on the roof, and they got a feed-in tariff. Well, that DC voltage from them solar panels has been stored in a battery, but when it goes back on the mains, that's using inverter technology like this to recreate a 50 Hertz sine wave, put it back on as AC. So again, there's high necessity for good filtration to make sure we get rid of much of those harmonics as possible. Another big cause of harmonics these days is the switch mode power supplies in computers. There's so many of them, UPS, uninterruptible power supplies, all that type of thing, is using this same flash on and off quickly technology to recreate a sine wave. Operations using ASD in the vicinity of sensitive electronic equipment, your cranes, yeah, should consider including either an isolation transformer or line reactors on the input of the drive to protect the other equipment from this potential problem. So installing filtration equipment. Yep. Okay, so that's my bit on inverter drives, just to give you an indication of the way the things that should be researching and the things you could consider, and maintenance, advantages and disadvantages and so on. Alright?